Hello again, welcome back to the second part of lecture 9.1. We've talked about temperature, what temperature is, what temperature scales we use. Now we're going to talk about thermal expansion. So continuing on with the idea of materials being made of atoms, those atoms having some kinetic energy, i.e. they're moving around, they're not just sitting perfectly stationary in their place in the object, they're actually moving because they've got this kinetic energy. Whether they're held in place or not depends on solid or liquid or so on. But that's the idea of temperature, is that they've got this kinetic energy. So a solid, it'll be vibrating on the spot. A liquid, it'll be flowing around within all the other liquid. And in a gas, it'll be flying around the entire chamber. So the state is just how much energy it has. It determines what it can do. Is it stuck in place by those bonds, vibrating, or so on. So with that in mind, with that mental picture of temperature, this next section of the lecture should make perfect sense. So back to the lecture slides, we will go to, so we talked about the 0th law of thermodynamics, was our last one in the previous video. So as I just said, we're thinking about atoms moving around in space. So if an atom, or all atoms in an object, get a bit more temperature, they get a bit more thermal energy, they've got a bit more kinetic energy, then they're moving around more. So as I said, they're vibrating in place. So when you've got a solid with these objects all in some kind of lattice, and they're bonded to all the neighboring atoms, and they're stuck essentially in that one location, they can still have kinetic energy in that they can move around within some sort of little space that they're allowed. Right? So they can't get too close to any of their neighboring atoms, but they can move around within that space. And so the more energy they have, the more they want to move around in that space. And if they get too much energy, then they actually start to make that space bigger. They push up against the other atoms. They keep sort of bumping into them, going, I need a bit more room. And if they're all doing that, every single atom in this solid object is doing that, then they're all just going to move slightly further apart from each other because they all want a bit more room. And that's exactly what we see happen. Every single atom moves a little bit further away from every other single atom, and so the object itself expands. They get further apart. So in order to turn this into some science, right, we've got the concept, we need some equations, we need some numbers, we need some way to analyze this and to be able to predict and then test these results. So we need to come up with terminology to define these changes. And all we have to do really is think about a length. You've got an object of some length, and you measure it, and then you heat it up, you give it some more energy, you change its temperature, you get a new length. So you can either talk about original versus new length, or you can talk about original length and change in length. They're the same sort of concept, whereas the new is just the original plus the change in length. So the object will expand. It turns out that this is actually linear. It's linear because every atom in that object is getting the kinetic energy, and they're all going to try and expand a little bit. And so if every single one of the atoms just expands one little bit, then the overall object expands however many atoms there are, little bits, right? So it ends up being a linear relationship. And we have what we call an expansion factor, or a coefficient of linear expansion. We use the symbol alpha, Greek letter alpha, to represent that. And that's all there is to it. You've got some original length, you go and change the temperature by some amount, then alpha times that amount of temperature will tell you how much the length will change. And so here's that formula. As I said, you can write it as either the final length versus the original length. So that's the LF equals L naught 1 plus alpha delta T. Or you can just talk about the change in length delta L, which is alpha L naught delta T. And you should be able to see how that works exactly into that previous equation. If you put delta L in place of L naught alpha delta T, then you see that the final length is equal to the original length plus the change in length, which makes perfect sense. Ignore the text down the bottom. That was going to be part of the thermal physics lab experiment, but not being on campus, we can't actually do that one, so you can ignore that little statement there. I may be able, if I can get on campus, I may take a video of that one as well, just for your reference. Units of alpha. From the equation, we can see that what the units must be. If you've got a change in length, that's going to be a length dimension. and you've got an original length on the right-hand side, that's a length dimension. So we've already got the units balancing just with those two values. So we've got a delta T and an alpha, and they have to cancel. Delta T is obviously going to be in temperature units, so Kelvin, and alpha, therefore, can be the inverse of that. It's got to cancel those Kelvin out, so it'll be Kelvin to the -1. We can use Celsius to the -1. This is a little sticking point for a lot of people. When you're talking about a temperature interval, it's going to be the same in Celsius or Kelvin. An absolute temperature, an actual temperature value is going to be different. You have to convert between Celsius and Kelvin using the 273 degree Celsius jump or 273 Kelvin jump to convert between. But if it's in temperature interval, then it's the same in Celsius and Kelvin. I might actually just draw a little number line as just an example. I want this to be really clear because this is a common sticking point. If you've got a temperature scale, so let's go with, let's just make some random scale. Hopefully those are about evenly spaced. Let's say that we've got, I'll do something easy, 10 degrees C, which means 10, 11, 12, 13, 14, 15 degrees C are these ones. Right? That's our Celsius number line. So this is some temperature. Right? Let's say that we've got some object and it was at 10 degrees C, and then we heat it up and it's now at 15 degrees C. So that means that we've gone from 10 degrees C to 15 degrees C. Delta T, the change in temperature, is 5 degrees Celsius. Right? And you can see that that's 1, 2, 3, 4, 5 steps. Right? We've gone up 5 steps on our Celsius scale. The other side of that, right, if this is degrees C, let's set this to Kelvin. Right? Now remember, to convert a temperature, you need to add 273. So that means that this is now 283 degrees C. And this is a good way to confuse everyone when I'm trying to explain it, to use the wrong units, 283 Kelvin. And that means that this, add 273 to this, so we're now at 288 Kelvin. So on the Kelvin side, we started at 283 Kelvin, and we went to 288 Kelvin. So we're still talking about the exact same object doing the exact same change in temperature. We're just writing it in different units. So this statement here and this statement here are exactly the same thing. Right? They are saying the exact same thing, just in different units. But that means that this object has also gone up 1, 2, 3, 4, 5 units. So delta T is 5 Kelvin. And so what I'm really trying to emphasize, what I want to make really, really clear, is that if you are talking about an actual temperature of an object, so an actual temperature, then you have to convert. You have to go 10 degrees C plus 273 gives us 283 Kelvin. You have to convert. And same with our final temperature. But when you are talking about a change in temperature, a change in temperature needs no conversion. Because, and remember, this is the bit that I mentioned when we were talking about the Kelvin scale, when he came up with it. He said, let's keep the same step size, right? Because one step of 1 Kelvin here is exactly the same as a step of 1 degree Celsius here. So the step size is the same. If you've got delta T is 5 degrees Celsius, then delta T is also 5 Kelvin. Right? The step size is the same, so a change in temperature is the same. But the actual temperatures you still need to convert. Okay. So hopefully that was obvious, and hopefully I've been talking for several minutes for no real reason, but I just want to make that really abundantly clear that if you have actual temperatures, you need to convert them. If you've got a step size that's the same, so Kelvin and Celsius, same step size, then a change in temperature is going to be the same in both units. All right. So back to our slides. That means that alpha can actually be negative C or, Celsius to the -1 or Kelvin to the -1. It can be either, because the step size is the same, so the change in temperature is the same. So alpha can actually cancel out a change in temperature of either of those units. That's can be a little confusing. Hopefully you understood all of that, and bear with me if you didn't. Just get used to it. You need to be able to remember that. Right, expansion coefficients. So this alpha tells us how much the length is going to change based on the change in temperature. And as you would expect, it depends entirely on the material the object is made of. So here are a bunch of examples. You'll notice that we've got two columns. We've got a linear expansion and a volume expansion. We haven't talked about volume expansion yet. I will. But you'll also notice that the solids are the only ones with linear expansion, because liquids and gases just take the shape of the container they're in. So it makes no sense to talk about their length expanding. Whereas a solid, because all the atoms are locked in place, then the length will actually change. So if it's got a length we can define independent of its container, then we can observe the change. So just looking at those, you can see that we've got aluminium 25 times 10 to the -6, and so on. That's not the largest one we've got. Lead is slightly larger, 29 times 10 to the -6. But they're all around about times 10 to the -6, or they all are in this case, in these examples. So they're all times 10 to the -6. So you can see that it's quite a small expansion, right? But it does happen, and we need to account for it. That is, in fact, exactly how thermometers work. So when you've got a thermometer, liquid mercury is a common one, the silver substance, but as we all know, that is actually toxic. It's hazardous to humans. So you'll now commonly see alcohol ones, such as the blue one in the background from this slideshow, or the more common red ones. They are alcohol-based liquids, which will expand very specifically. And so using thermal expansion, we can see how much volume change there is, in this case, by measuring it up a little thin tube. If the volume of that mercury increases, then that's going to expand, and it's going to go further up that tube. And we've got a preset scale that tells us exactly how much expansion equals how much temperature. So that's a useful method for measuring temperature, and it relies on this idea of thermal expansion. Unfortunately, we get thermal expansion in places we don't want it as well, such as train tracks. Those are the more common one, although modern technology, or modern designs rather than technology, is allowing for that. So it is becoming generally less common, but it does still occur when we get hot enough. Train tracks become warped, so they're trying to increase in length, but they can't, because the next bit of track is up against the end of that one, and so it increases in length by becoming wobbly, right? If you don't have a straight line, you can become longer. So that's what happens with train tracks and heat waves, and obviously that's a bad thing. That does mean we have to be aware of this. We have to allow for it when we're designing objects. So newer designs allow for thermal expansion. The right-hand photograph there shows overlapping train tracks. So here, rather than going end to end, the train tracks now overlap each other, and that gives us plenty of room for that track to expand, because if it does, it'll just go along beside the new piece of track rather than pushing into it and causing the buckling. You'll also see on bridges that they have usually sort of a tooth, tongue and groove, or a tooth type setup, as per that first photograph, and that's again to allow for that expansion. Because bridges are usually a set length, you know the maximum it could possibly expand, so you can allow for that. Because train tracks get so long, that's why we need the room for unlimited expansion by going past next to it. Not as much of a problem with bridges, because they can't really get unlimited expansion. They're a fixed length, they can only get a certain amount longer. And you'll also see it in buildings where you've got a brick wall, but then it'll have a little gap, and they usually fill it with a soft substance, so it's still watertight and airtight. Yeah, well, not necessarily airtight, but at least watertight. And that allows for those bricks to expand and contract as well, leaving a gap between them. You'll see it when driveways are laid down. Concrete driveway, they'll go and they'll cut lines through it. That's not just for patterning, that's so that they can expand, the concrete can expand without cracking. As an example of all of this, let's talk about an example. We've got an iron ring with an internal diameter of 6.420 centimeters, and it's at 20 degrees Celsius. We also have a rod of diameter 6.445 centimeters at 20 degrees Celsius. So the ring is slightly smaller. The inside diameter of that ring is slightly shorter than the rod diameter, so it can't fit onto it. So for it to fit over it, then we need to increase it till it's larger. And for it to fit comfortably, it actually needs to be slightly larger. It can't just be exactly the same size. If it was exactly the same size, then the atoms would be trying to be in the same place. So we've got to get it slightly larger than the rod, and it needs to be 0.008 centimeters larger in this case in order to fit on comfortably. So if we keep the rod at 20 degrees Celsius, we're not changing the temperature of that, so that 6.445 centimeter diameter is set. We're not changing that, but what we're going to do is we're going to heat up the iron ring so that it expands, and we want to know how hot we have to get it in order for it to then be able to fit over the rod. So that is the question. It's just a simple calculation-based question. I will switch to a new, I can probably fit it all on here. So we're going to try and calculate what temperature we have to get to. So we'll write out, as usual, start by either drawing a diagram or writing out what you know. So we've got a rod here, and it is 6.445 centimeters. And we've got a ring like this, and the inside diameter, that's the one that we're concerned with. The inside diameter is 6.420 centimeters, but we need it to be 0.008 larger than this one. So we need it to be 6.445 plus 853 centimeters. That's what we need to get it to. So this is our L naught, our original length, and that is our final length, right, 6.453. Therefore, the change in length that we need is going to be the difference between these. We need to go from 0.420 up to 0.453, so 0.033 centimeters. That's the change in length that we need. And the question is saying, what temperature do we need to get this? And it tells us that for steel, iron, it's an iron ring. For iron, we have 12 times 10 to the negative 6 kelvins to the negative 1. Or, remember, that can be Celsius to the negative 1, degrees Celsius to the negative 1, same thing. So now we can just use our equation. Right? Our equation tells us that the change in length for some object is just going to be equal to the original length times the expansion coefficient times the change in temperature. And since we're looking for this term, we're looking for the change in temperature term, we can just rearrange by dividing both sides by L naught alpha. So we get delta T is equal to change in length that we want over the original length times alpha. And we know all three of those things. Right? We know the original length, we know that, we know alpha. So now it's just a matter of using your calculator. Hopefully you can all manage that. The change in temperature we get is 428 Kelvin, or again, degrees Celsius, either or. Because it's a step size, we can use either unit as acceptable. So that's the change in temperature, but the question was asking us what is the final temperature we need to get the ring to. So temperature final is going to be temperature initial plus change in temperature, which is 428 plus, remember they started at 20 degrees Celsius. So 448 degrees Celsius. At this point, 448 degrees Celsius is not the same as it was in Kelvin. Right, so the step sizes we could write in either, but this final temperature is an actual value, it's an actual temperature reading, so we would need to add 273 to that to make it into a Kelvin reading. But as it is, I'm just going to leave it as Celsius, degrees Celsius, since that's what the answer was given, the question was given to us as. Jump back to the slides. So there again, solution is printed in the slides as well for you to work through. The common question with that example is about it being a ring. We've just taken the diameter and we've said that that's going to change according to our linear expansion equation, but a ring isn't a rod, a ring isn't a straight line. How come it still obeys by that linear expansion equation? A lot of people expect this situation to happen. They expect the ring to expand across its width. Right? So they expect this width from the inside of the ring to the outside of the ring to get wider. And so they think that the inside of the ring will actually get smaller. Right? That loop, that hole, will get smaller because the ring has gotten fatter. And if the ring did just get fatter, that would happen. But of course, the ring doesn't just get fatter. It gets fatter and it gets bigger. And the getting bigger is more than the getting fatter, so that the opening actually still gets larger. Now, yes, that can be a little confusing and it can be difficult to visualize. That's why we just trust the equations. They have been proven to work. We know they are correct. But if you really want to convince yourself of this, think about every atom that's lined up along the inside of that ring, the very inside ring of atoms. So the very inside of that loop, of that ring, and there's one line of atoms that goes all the way around inside that circle, so the very inside edge of the hole. Those atoms, if that ring got smaller, those atoms would be getting closer together, but the whole thing is getting hotter, and we said that when things get hotter, the atoms are trying to get further apart. So that means that that loop of atoms actually has to get bigger so that they can all get further apart to allow for the increase in temperature. So the hole in the ring does still get bigger by that exact same linear expansion coefficient equation. Hopefully that convinces you all. Feel free to do some more reading or do some more thinking about that if you're still uncertain. But just believe me, it does, right? The hole will get bigger and the whole ring will get bigger and it will get fatter. Everything increases, right? A common use, this is just often used as an example. It's a common use for differing coefficients of expansion. If you've got two materials with different expansion coefficients, so in the picture here, we've got steel has an alpha of 11 times 10 to the negative 6 per Celsius, and brass has 17 times 10 to the negative 6 per Celsius. That means that as the temperature changes, they've been forged into one strip. Right? So we've got a layer of steel and a layer of brass, but it's been merged into one solid object that's now half steel, half brass. As the temperature increases, then the different halves of that are going to try and expand different amounts. The brass is going to try and expand more than the steel would, and that results in a curved shape, because when we're curved, the inside half is now shorter than the outside half. So the different coefficients of expansion force it to start to bend. And this was a common device for thermostats. Obviously, a lot of modern ones use computers and other temperature sensors, but before that, and you can still find them, they would use these sorts of strips. And what would happen is that you would tell it how hot you wanted the room to be, and when you adjust the knob, it would be moving the position of this, so that when it got to that temperature, the strip had bent around enough to complete a little circuit and turn off the heater. And then as the room started to cool, if it cooled too much, that the strip would uncurl a little bit and it would let go of the switch, and that would turn it back on. So it was sort of an opposite switch in that sense. But the idea, the actual specifics don't matter too much. The idea is just that you could use how much it curved as an indication of what the temperature was. So it's just a common little example, just to show you the sort of things we can do when we know these different expansion coefficients, and we can come up with some systems that exploit these. So as promised, we have volume expansion as well. We've talked about linear expansion, the length of something changing. We also have volume expansion. In this case, the formula looks exactly the same, but we have a different coefficient. We have beta for volume expansion. So alpha was for linear, beta is for volume. But other than that, the formula looks exactly the same. The change in volume is equal to the original volume times beta, our coefficient, times the change in temperature. And so it's exactly the same equation. You will often see that for solids, that beta is about equal to 3 alpha. And that's because if you've got alpha expansion in each direction, then you've got 3 lots of that become beta. Don't worry too much about the math. It usually works out about right that beta is about 3 alpha. But you should always look them up. Don't just assume it's going to be 3 alpha. The next thing to think about is tying it back to something we talked about. We talked about stress of an object due to a change in length. If you compress something, then you're putting it under stress, and we need to know that objects can withstand that stress. And if you've got an object that is heated, it's trying to expand. But if you've got an object that's heated and tries to expand but can't because it's part of a building or some other structure, then that means that it's trying to now be longer than it is. So in effect, it has been squashed from where it should be if it wasn't under compression. So what we have is compressive stress as a result of thermal expansion. And the expansion hasn't actually occurred, right? But the object has tried to expand. It's tried to expand. It couldn't because there's stuff in the way, so it's under stress now. If you need to picture this, you can think of it as two steps. Imagine taking the object out, heating it up. It now gets to a certain length, a longer length, and you now have to squash it to put it back where it is. All right, so you can think of it in those two steps if you want, if it helps you visualize it. But essentially, this object, without changing at all, has now become compressively stressed. And we need to know how much stress it is under and be able to calculate the strength of compare it to the strength of the object and make sure that it won't fail. So this comes down to, again, going back to engineering and making physical things, we need to make sure that it's not going to break within the normal temperature variation you could expect. So within normal atmospheric temperatures. To calculate that, we've got an equation for thermal stress. We all remember, of course, that stress is force over area, which is also pressure, but our stress is E times epsilon. So E is our Young's modulus. Remember, Young's modulus for our material determines the amount of stress per unit strain, and the epsilon is the strain. The epsilon, of course, is delta L over L naught, but we've just been talking about delta L and L naught. We've been talking about the original length and the change in length due to temperature. And that change in length due to temperature, how much it wants to expand, is effectively how much you've compressed it by not letting it expand. So that means that we can put all of that together, and we get that the stress is equal to delta L over L naught times our Young's modulus. But we know that delta L is equal to alpha L naught delta T. That's what the equation we just talked about. So that means we can put that in for delta L, and now we've got an original length on the top and bottom. We can get rid of that. And we get out that the stress is equal to alpha Young's modulus change in temperature. Right? So just those three terms. So what you see is that it actually doesn't matter how long the object is. The compressive stress, the thermal stress, compressive stress due to a change in temperature, is going to be the same for any object made of the same material. And that's because the longer the object is, the more it would want to expand, and therefore the more it compresses. And because those are related linearly, the original length actually ends up being immaterial. It doesn't matter. All that matters is how much it wants to expand, alpha, and how much it suffers stress when it's compressed by that amount, which is the Young's modulus. And then obviously the delta T tells you how big those values, how much change in length you're stopping it from doing. So that is thermal stress. We can then compare that to all our same strength, ultimate strength tables as we had for when we looked at stress and strain. So it's the same concept, same equations. All of that's the same. We're just now looking at the temperature change being the cause of that stress. The exact same thing happens the other way around. Right? If it cools down, if it gets too cold suddenly, or not suddenly, but if it gets too cold, the object is now trying to contract. But of course, in a building or a structure, it can't contract. It's held together. It's holding two other things which keep it at that same length, and you get the exact opposite thing happening. And the stress is still going to be the same. Right? That's now it's now under tension, tensile stress. But the equations all the same, the values all the same, as we saw Young's modulus, alpha, all generally the same for compression and tension. A couple of objects, a couple of materials, compression and tension are different. So you need to be aware of whether it's heating up or cooling down for these equations. But in general, for most things, Young's modulus is the same, alpha is always the same. So we have those same equations. I've got another slide for that, but I've already just said all of that. Linear models are based on empirical evidence. So empirical means we go out and we actually measure stuff. We do things. We just gather data. A whole lot of data collected means we can then start to build up these relationships. We can determine the values for alpha and beta based on all of that information. These values aren't fundamental. They're not derived from some fundamental laws, right? So acceleration due to gravity on Earth, 9.8 meters per second, we know that value from measurement, but we can also derive it from the universal law of gravitation by putting in the mass of the Earth, the mass of the object we're talking about, and the distance from the center of the Earth to the object at the Earth's surface. We can figure out that value from that law of gravitation, but there's nothing like that for these linear coefficients of expansion or volume coefficients of expansion. It is just gathered from data, it is observed, it is measured, and these happen to be the results. So that's all the theory content. As usual, there's a review slide. Do read through that. Make sure you're happy that you've remembered all of those bits of information. There will be a third video coming up shortly, which will have the questions. As I said, there are quite a few for this one, just because we've covered quite a bit of material here. We just want to drill some of that stuff home. Make sure you're happy with all of that. So that is the end of topic 1, lecture content, and stick around for the questions.